All righty, up and running. Hopefully this is an interesting discussion. It's meant for, not sure, teachers or students, whoever's interested. I don't think I would probably give this lecture to I don't know, maybe an honors class could sit through it, but it's hard to maintain your focus and follow things when they're presented in lecture format. But I'm going to talk about completing the cube, its ramifications from a holistic standpoint, many topics that you can discuss and ideas to put in front of students, and going to have at it. It's going to be from geometric, numeric, graphical, and symbolic perspectives. I'll be touching upon graphing forms for cubics. I'll be touching upon integration and differentiation, average rates of change, a whole bunch of things. But I think really at the heart of this is the completing the cube process, and trying to understand that from a geometric standpoint, I think is very helpful, so that you're not just doing pure mechanics. I think that, chapters on cubics should be rewritten. Rene Descartes' rule of signs and things like, oh, good stuff, but I don't think it gets at the heart of what's going on, and that's what this video, I hope, is about. So I'll have at it. I've written out everything. God, I hope I don't forget to, so many things I want to say. I'm going to try to slow myself down, and just like my classes, when we get into conceptual work, I don't expect any understanding the first time you hear something. So I start my classes day one in a calculus class. I do integration and differentiation on day one. And I do it because those are the major topics of the course. And I want a conceptual understanding. And that gives us a chance to talk about it for the rest of the semester and build upon, some of those initial truisms, which I hope to show a few of today. All right, so let's get into it. Let's talk about cubics. And let's try to use user-friendly numbers. And I hope I've got the boards the way I want them. Make sure that I can see everything this time. Okay, pretty much. All right, I'll try to change this around as necessary. All right, so let's get started with stuff we know. Geometric. -3, -3, -3, -27. -2, -2, -2, -8. So what do we got? We got side length to volume. And you can say, well, can volume be negative? Well, we want to introduce negative numbers so that we can work more efficiently and study more problems. So I'm not quite sure what to call a negative side length and a negative volume, but hey, maybe the language will improve as I keep talking about it. So we can see that -27 to -8. It's going up numerically 19 units, and -8 to -1, going up 7 units. Then we got a 1, we got a interesting situation here. All right, 1 to 8, 7, and then back to 19. So it looks like, things are changing in a positive direction. And, if we look at cubics from a graphical standpoint, and we just, plot a couple of user-friendly values, and then think about the average rate of change from, this was what? This one was -3, -27. And then this one was -2, -8. Okay, well, average rate of change, get a little feel for what the cubic looks like from a rates perspective, right? From a rates perspective. And again, this seems like a unique moment right here. It seems like that's where it's going up least quickly. Right? That's where it's going up least quickly. It's slowing the increasing process down and then speeding up. And I think we can see that it's not changing here. It's kind of flat. And we can introduce concave down, concave down, concave up interval. And so we talk about points of inflection. All right, so we got some interesting conversations going on. And now let's dive in a little closer, because if I connect this as an average rate of change, Well, we can see that initially I'm not going up as fast as this slope. And then I'm actually going up faster when I get to 2. Right, so that's just average rate of change. So what's going on at 2? Well, let's take a look at it numerically first. All right, so let's get a little numerical perspective. And this is only algebra 1 here. Y2 minus y1 over x2 minus x1. But we can see that the change here is 0.01, 001. So the change in x is 0.001. And that's pretty small change. It's kind of like taking a microscope to algebra 1, but it's still algebra 1. But, you know, for folks who are teaching calculus, we're already starting to mimic a little bit the concept of dx. You know, very small change in x. All right, so let's look at where this changed least quickly. 0, 0, 0.001, you multiply it out, you know, and you're cubing. I think I just butchered that one. 3 decimal places should be 9 decimal places, right? 3, 6, 7, 8, 9. Well, I don't know how you're going to describe this change, but I'd say it's pretty minuscule, like it's not changing at all. Whereas I can use 3 decimal places here. There's a nice pattern here. There's a really nice pattern there as you do more and more. And I usually go after that pattern by having the class go to the board and doing, you know, if I got 16 students, then we might do -3 to 3 and then look at it and come up with the pattern that's established here, which I'm sure calculus people might recognize, 0.012. The 6 is really 3 times the x value. It's really 3 times the x value. And I'm coming at this from a one-sided limit, of course. So it's approximations. But we really have 0.012 plus 0.00006 plus 0.0000001. So if we're looking at how this is changing, you know, we're really looking at that divided by 0.001, which is 12 to 1. So at this instant, at 2, where's 2? So I think that's where 2 was. We're going up at a 12 to 1 rate. Okay, roughly. That's what the numerics say. Now, how about geometric? What's going on geometrically? Well, there's my trusty box. Oh, I hope I have the camera on. Sometimes I get talking and I forget to move the camera. But, okay, let's introduce a little calculus. All right, so here's a post-its in there. So here's a box, and it's a perfect cube. Let's say that the dimensions are 2 by 2 by 2, length, width, and height. All right, and that's got volume, 8 units of volume. Well, what happens when the cubic gets a little bigger? Well, 2 gets a little bigger, maybe to 2.001. And I'm using this little layering process here, right? I'm adding a little volume to the front side. I'm adding a little volume to the, let's do it this way. Yeah, let's do it. Well, I guess I just have to do it one way or the other. Front side, this side, and then underneath, if I can get it to, right? So I basically kept the same shape, but now the volume has just increased to an approximately at a rate of 12 to 1. And what have I really done? Well, I mean, what are you looking at? You're looking at a square, you're looking at a second square, and you're looking at a third square. And what is, square area? This is 2 by 2. Well, then that's 4 units of volume, area, 4 units of area, 4 units of area, 4 units of area, but we're adding volume. So where's that missing dimension? It's the thickness, right? That I'm using this to describe the thickness of 0.001. And of course, I can make it even thinner to get a better accurate. How's it changing in an instant numerical evaluation? But this is going to be standardized. Now, I should have taken more time with making more of these layers, right? But let's just say you just kept layering and layering and layering. Well, the box is growing, right? And at what rate? Depends upon the layer. Okay, so I didn't put this down, but let me, so that's to geometric, just a little understanding. So let me just cube 3. And 3 cubed is 27. And let's try to cube 3.00001. So let's see, that's 5 decimal places. All right, so that's actually going to become 27.12345. 1, 2, 3, 4, 5. And 3 times 3 is 9. 1, 2, 3, 4, 5. And then we got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, that's more accurate, more decimal places, right? And I'm trying to start students understanding what dx stands for. All right, you can think of it in this case as the thinness of the layer, but that's a dimension, and so is that. And so 3 dimensions, length times width times height. All right, so can we agree that 10, 100,000, 10,000, 100,000, this is 100,000 times smaller than that? So you can start to talk about the limiting process a little bit in your classes. And if I divide by 0.00001, well, that's a 27 to 1 rate of change for the cubic, which might, be going up right at this instant at about 27 to 1. Okay. All right. And what are you going to teach in your classes? Y equals x cubed. Y prime is 3x squared. Oh, yeah. What are you looking at? You're looking at 3 squares. And that gets you area. Well, what if you wanted to go, say, from 2 to 3, adding up all those layers of volume change? Because that represents the volume of this one layer. And where did that rate of change come from? It came from, let's get this out of there, let's get that out of there. It came from the cubing process. And from 2 to 3, you're already talking of the first fundamental theorem of calculus, right? 27 minus 8. Oh yeah, 19 units of change. Yeah. That's how much the volume increased from 2 to 3. All right, so got a little messy here. So let's go now and talk about where this all comes from in a pre-calculus standpoint. All right, so let's see if I can get this board in front of this one, maybe. Okay. All right. Let's get this up a little bit. Okay, let's see what I put on this board. Hope I'm doing this in the order that I wrote things in. All right, so this is what you generally study at the algebra level, the roots. Well, that's not the exciting part of cubics, by the way. It helps us understand a little bit more about cubics. So I got a canned expression here, 0, 2, 10. So we can see the roots at 0, 2, and 10. It turns out the point of inflection is at 4. And the reason it's at 4 is because the average of the roots, 0 to 10 divided by 3 equals 4. And that's minus b over 3a. All right, got to explain that a little bit more as we go along. So I multiplied this out. X times x squared minus 12x plus 20 gets me x cubed minus 12x squared plus 20x. And we want to look at graphing forms. And I'd like to get a better sense of the point of inflection is really where it changes from concave down to concave up. That's the most important place on this cubic. It's more important than the roots. And the rate of change here as well. We can find that without calculus. We're gonna, all right, in this video, we're gonna. But if you look at from a graphical standpoint, where did I do this? Yeah, from a graphical standpoint, let's take a quadratic, x squared plus 2x plus 3. Well, that's 3 graphs, x squared, 2x, and 3. Okay, well, that's helpful. What can we glean from that? Well, it'd be nicer if I didn't have to consider adding 3 graphs together, and students probably don't even know what that means the first time they hear it. But when you're adding graphs together, you're really looking at the y values and adding them all up. And it would be nice if you only had 2 graphs to consider rather than 3. And that's what completing the square is. Completing the square is reshaping this. I should have gotten something for factored form, would have been a little bit interesting to talk about that right now. But when you do this out, right, you can immediately see that you get x squared plus 2x, the first two terms, right? Then all you got to do is make an adjustment. And, you know, square one, you get 1 plus 2 is 3. We can see that this is true. And if you add these things up, well, you want to not only add the y values, but you want to add the rates of change at those instants. All right, so a constant, no rate of change there, right? And if you think so, give me a call. We got some help for you. And at x equals 0, the quadratic term isn't changing at all. Why is that? Well, if you square the area, 0 times 0, there is no area. There's no area, so I can't change much, and that brings us right back to, you know, that, well, where the heck did I do it? 0 changing to 0.001, and then we had 9 decimal places. That's not changing. Why? There's no square. And that's going to lead us into the completing the cube process, because, you know, where does a cubic change least quickly? It could be negative, you know, negative number is small, you know, -10 is really smaller than -9. So it's changing most rapidly, or least rapidly. I'm not sure what language to use there, but at -b/3a, that's happening. Why? Because we're going to complete the cube. Okay, and here's that. Okay, but over here, one more time, it's not changing there. Well, if you added these three things up, then you're here, right? Because those are both 0 and that's 3, right? And we can see that moving this up brings us to 3. And the only thing that we have is the rate of change of the linear term. And so it's, you know, if I add up the rates, I've still got to be going up at that instant, right? And if it's positive quadratic, then we get that cup shape. And so, you know, you get something that looks like, oh God, I've lost myself in my thought process, but so let me just keep going because I really want to get here. So what happens when I multiply this out? Well, I did multiply it out somewhere. Do I have it? Yes, x cubed minus 12x squared plus 20x. Am I capturing all of that? Barely. All right, so that's what you get when you multiply this out. And if you look at it from the right to the left, which students should get practice doing, again, this would be a homework assignment. Watching this video would be a homework assignment because it's hard to maintain your focus this long. Somebody's just rattling on. That's why I put my students at the board. But if you put a 0 in, we can see that, you know, we're at the origin. Immediately see that. And if we look from right to left, you know, when I cube something like 0.001, that term is exceedingly small, and so is that one. This is where the change is coming from, right? This is the most important term when we look at local behavior to end behavior. Right? Some nice terms there to talk about. And so what do we have next? The second most important term influencing this is concave down, right? And then all I know is it's going up and it's continuing to go down in terms of end behavior, but I start to get a little feel for the graph. All right, how do I get a better feel for the graph? Completing the cube. Okay, so if I do x minus 4 times x minus 4 times x minus 4, I think I did it out somewhere, but the first two terms are x cubed minus 12x squared, right? And that nails the first two terms here. The rest of it is a little bit of factoring. And, you know, I'm trying to get back to ax cubed plus bx squared plus cx plus d. And if I did this out using the letters, right? Using the letters, I know that I have a times x plus b over 3a, which I'm going to call h from now on. I'm going to call it h, just like hk. With quadratics, hk is going to be the point of inflection of the cubic, right? So that gets me the first two terms. Well, I've got some linear factoring that I've got to do. And if you want to see that and where it came from, then that's where you go to graphing cubics. It's a video somewhere in the videos I've done. All right, but this is starting to get messy. But let's just go back to numerics for a moment. If I put 4 in here, I get 64. And I didn't do this out, so you can check it, but I'm pretty sure it's minus 192 because there's a 3-to-1 ratio and opposites. And that's got a geometric reason. All right, and the quadratic at the vertex, it's 2 to 1 and opposite. So all I did was double this and change the sign and add 80, and I get minus 48. Well, that turns out to be the point of inflection, 4 comma minus 48. I haven't checked this work. So if anybody checks it, write back to me if I'm wrong, if I made a careless error, but this is sound consideration. All right, so the only thing here is, what's the formula for this? Well, we got to get CX, and it turns out it happens to be, did I put it somewhere? Am I changing where I'm going? Let's see, I'm going to change this one to, I'll be right back. Let me just flip these boards around. All right, so that's going to be at the end of this video. I got a little challenge for everybody. Might as well show it right now. I'll do it out for you in a little while. But let's say we have a point of inflection at 5.7. You're going down at that instant at 10 to 1, and it also goes through 940. It's a 5-second calculation that you can write out the equation of that. That's going to be one of our things to do right at the end of the video. Now, where did I write where I want to go with this? Let's see if it's on the back of this book. I would be in my classroom and I would be moving around the room differently, but it's being used at the moment, and I wanted to do this. So let's see, what do I have? Well, I did put this on there, so I might as well show it. It's talking about the rate of change at the origin. All right, so you got tug of war here. X cubed, when you go to 0.001 is contributing a very small upward influence. Minus 12x squared is contributing minus 0.0012, and 20x is contributing 0.020. Okay. Well, I think you can have a discussion and talk about, the fact that those are infinitesimally small numbers, and the real change is here. And then if you divide that by 0.001, well, then whatever the polynomial is, when you finally get to the end, and I'll just write EX plus C, I don't know. EX plus D, EX plus F, A, B, C, D. Doesn't matter. Whatever the polynomial is, the last two terms are the tangent to the y-intercept. So that's good to know. Because of this, you can see it. You don't need calculus. You can see it here. All right. So quick generic sketch. So again, I would start at 0. I know I'm going up at 20 to 1. I know I've got a little downward influence and end behavior, right? So we start to get a little better sense. It would be nice to nail that point of inflection, and it's really easy to do now because it's minus b over 3a that gets you the x value, and all you had to do was put 4 in here, right? And like we did to get the y value. Turns out, okay, I don't know where I put it, but algebraically, without calculus, you can find the rate of change of the linear term by c minus 3a h squared. All right, so that's what gets you the slope, whether it's positive or negative, gets you that slope. So let's see now. Okay, so this is where I'm going with this. Can I turn this around? There we go. All right, let's see if I can get you to see that. All right. Yeah, so I wrote it here, right? Okay. So did I talk about the integration? I think I did. I think I talked about that, but I don't think I talked about it from a graphical standpoint. All right, so so you got 3x squared. So this is 3x squared. Right? And what is this little rectangle here? Well, that is really a little change in x. That's capturing the area under this curve. And the height is 3x squared. Right? And so that, back to geometric situation, that little area with a change in one of the dimensions is getting the volume. So that's really this. And if I wanted to get the next layer on top of this one, then obviously it would be a little bit better, a little bit bigger. And if we kept doing that from 2 to 3, well, that's what's capturing those 19 units of area. That's the change. All right, so you want to link those geometric principles early on in the term so that when you get to more difficult functions, you can extrapolate to any graph. All right, so that's just a statement I wanted to make. All right, so why don't I do, what did I want to say? I always end a video and I'm like, I should have said 4 or 5 more things. Maybe I should just take you through one of these very quickly. So if this is a cubic, and this is the linear term, we've eliminated the square term, so we have fewer things to think about. So if I was to add, let's add this to that. Okay, well, we're no longer flat at the point of inflection, right? We're going up, so we would get a graph that's always going up. But if I brought it in a linear term that was negative, then adding those 2 graphs would get me something like this. And again, the cubic is flat. And why is the cubic flat? Because completing the cube got us x minus 4 cubed, which means that if I go from 4 to 4.0001, then 4 cubed 64, and this one is 64 point, what is it, 3x cubed, so 3x squared, 16 times 3, 48, so that's going to be 0.000, I think I missed the 1, 2, 3, 4, 1, 2, 3, 4, 48, 1, 2, 3, 4 times, 3 times 4 is 12, and then 4, 1, 2, 3, I'm pretty sure that's the right number. You know, we're taking on the change, which is, you know, in this case, 3x squared, and that's the derivative of x cubed. So I mean, there's lots of very weighty things to talk about here. Maybe I'll just do one very quickly. Let's see if I can do a canned, how quickly you can look at cubics in graphing form, and what we can learn from that. And you can dive into the cubics in graphing form video, which spells it out more slowly and carefully. But right now, I'll just make one up. So let's go 2x cubed, let's make that 6. So let's do minus 6x squared plus 10x plus 5. Nice round numbers. Okay, so graphing form, 2x cubed, x, boom. Okay, now minus b, 6 over 6, 1. So minus 1, minus 1. So now I put 1 in, and that's just going to get me minus 4 plus 6 plus 5 is 11. And then all I have to do is c minus 3ah squared. C is 10. Minus 3, a is 2. H is 1 squared. And so we get ourselves going up at 4 to 1. All right, so that is that, which means I now know that I'm always just going up. And at the point of inflection, I'm going up at 4 to 1. And the point of inflection is 111. And I wanted to do one that was a little bit different. So let's make that minus 10. All right, because I wanted to show you how you could get the x values of the local max and local min more easily. So c minus 10 minus 3 times 2 times, what did I say, 1 squared. Okay, so minus 16. So this is better to look at. So now I know I have, you know, 1 always increasing, always decreasing, the rate of change at the point of inflection. And then I want to do it from the calculus standpoint. Y equals 2x cubed minus 6x squared minus 10x plus 5. Okay, so I now know I have one of these. I know that's minus 16 to 1 right there as a rate of change. And I know it's still 1. No, I got to put 1 in and get a different y value. So minus 4 minus 14 plus 5 is minus 9. So I now know that that's 1 minus 9. And it turns out that the x value here is coming from 1. We're measuring kind of like quadratic formula. In this case, we're moving backwards, minus, and it's all about the interplay of the rates. And so that's the opposite of the rate of change over 3 times the a value. All right, and I think I talked about that. And this one, of course, would be the plus. You know, the x value here would be 1 plus rate of change opposite over 3 times 1. Oh, 2. This was a 2. Excuse me. That was a 2. Okay, so that's a 2. And that gives you those x values, and you don't need a calculator. You know, you get those pretty quickly and easily. All right, so this is the graphing form for a cubic. And let's talk about the rate of change of the tangent at the point of inflection. Very standard question, right? It's quicker and easier to get it this way, but so let's start with y. Let's look at y1. I hope this matches, because if it doesn't, then I gotta tuck away this video somewhere. So there's your 6x squared minus 12x minus 10. And at 1, hope you see you have 6 minus 12 minus 10. That's what you get. And so if you do that, you get minus 6 minus 10, which is, yeah, minus 16. That's what we said. Okay, and you also have the 2-to-1 ratio there. That only happens at the vertex. And so what's that mean? That means we have a cup shape up, and at 1, negative 16, that's the minimum value. And what do we have? We've got, or I guess I erased it, but don't we have a cubic that looks like that? And am I not going down there at a smallest number, a minimum? That's the minimum rate of change. I'm increasing, and then I'm eventually going down at 16 to 1, and then it's 15 to 1, 14, and so on and so forth down. So that's interesting. And then, of course, if we have y double prime, we get 12x minus 12, right? When's that equal to 0? And changes signs, concavity, you have those discussions, right? From the calculus standpoint, we can see 1, all right, which is really minus b over 3a. Right, and we used to have 4 terms, now we have 3, so it's easier to see graphically the interplay of those 3 terms. All right, so tangent, that's a typical question, right? So what do you have? You got minus 16, x minus 1, what did we say the y value was? Not minus 9. That's the tangent, yes? Well, is it a stretch to put an x minus 1 and a 2, and that's a cube and a 2 there? Well, from a calculus standpoint, there's the interplay. And I think that's important to discuss and to look at. I'm sure there's more I want to talk about here, but you know, that gets into more calculus. I'm looking at this from the geometric, numerical, and symbolic, graphical, all that, those perspectives in a pre-calculus way. Trying to get comments, I guess I should put myself in the screen, trying to get comments, get kids thinking about this stuff much earlier. You know, I would blow up the system of sequential. I really would. I'd start in kindergarten. Every day I'd talk a little bit of number lines, maybe a little addition, maybe a little more, and keep an eye on how kids are coming. And once they master something, you know, throw another 5 or 10 topics at them and give them as much time as they need to master them. I guarantee you, kids are going to know how to multiply, add, and subtract fractions when you're done with that. And they're going to have a better number sense. And if that's the case, then you can get at this stuff earlier than calculus. I saw an MIT grad talking to 5th graders a week or so ago on YouTube, and I'm all for what he was doing. He was just, you know, using shapes, and I don't know if he used a cube or not, but, you know, he's working with entry-level concepts that get kids thinking about this stuff sooner, because my experience learning calculus was not enough time to understand what I was looking at. You know, it wasn't until I started teaching it and asking myself, what's really going on here? You know, that all of a sudden it started to make sense. And, you know, I had great motivation. I'm a teacher, so I had great motivation to try to understand what's going on. So it took me, you know, a long time to really understand integration at a much deeper level and differentiation. And I think you got to tie it to geometry. So I'm rambling now. I said most of what I wanted to say, I hope, and I'll put this out there. And I tried to turn comments on to the YouTube channel because I never get any comments, and I guess it was off for the longest time. So if anybody has any thoughts and they want to share or talk about what I'm doing, feel free. You can't hurt my feelings. I'm too old. All right. So, okay, I'm sure. Oh, I wanted to show you the last thing was the answer to this question. All right. So what do we have? All right, well, we basically have, do we have the only thing we're missing is the A term, right? The only thing we're missing here is the A term. So we got the x minus 5 cubed. We've got rate of change minus 10, x minus 5. And we got 7. So I guess, you know, we're just trying to figure out what's going on with the A term. Well, the only way that we can put a, you know, get 40 out is to put 9 in. So 9 minus 5 is 4 cubed 64. Let's get rid of that. Get rid of that change. Because we just want to go up 9 units, or 7 to 40. We went 33, right? We just want to go up 33 units. All right, but I also got to put 9 in here. If I put 9 in here, I'm going down 40. Well, let's get rid of that right here. I'm done. All right, so what is it? It's the change in y plus the opposite change of the linear. I don't know how I want to say that. Did I even show you that? No, I guess I have to do that again. All right, so let me do it again. I'm not going to remake the video, and I apologize for that. Maybe I'll get better with repetition. So 5, 7, yeah, from scratch. Well, if we know the graphing form, then we know we've got x minus 5 cubed minus 10 times x minus 5, and that is 7. And you don't need calculus here. So drop in a 9. 9 minus 5, 4 cubed, 64. We don't want that. We want to go from 7 to 40, which is up 33. Okay, but over here, right, this is completing the cube, so there's no rate of change here. Rate of change is over here. And if I drop a 9 in, well, it looks like I'm going down 40. No, I don't want to go down 40. So why don't I write plus 40? And that negs this change. And so that's the A term. In this case, it's 73 over 64. 73 over 64. What's the 64? That's the change in x cubed. That's the change, right, from 5 to 9 is 4 units. I should have gone up 64 units, but the linear is taking me down 40 units. It's taking me down 40 units, so I got to neg that in order to get the, I want to go up 33. So there's some conceptual considerations there. And I think it's useful to have these discussions, but probably for an honors class, I don't know. If you sign up for homework, some of the kids in class are going to look at it, take some interest in it. Some aren't. But, you know, if we're trying to push kids in a forward direction, this is what's going on. And I think it's more important to study this, the interplay of the terms, than it is, you know, doing more factoring and stuff like that, which is purely mechanical. All right, that's it for me. I'm going to post this. And again, if you have any comments, feel free to make them. Bye-bye.